We are in lecture 20 of the course Computational Hydraulics, and this is module 2, numerical methods. And this particular lecture class will be discussing unit 16, that is mesh-free methods overview. In our previous lectures, we have covered finite difference method and finite volume method. Now, we will cover this mesh-free method. Learning objectives for this particular unit: at the end of this unit, students will be able to define sheaf functions, and they will be able to construct polynomial basis for function approximation. Domain representation. Let us consider a general domain where we have Neumann kind of boundary, Robin kind of boundary, Dirichlet kind of boundary condition. This is internal domain. Again, phi 2 is another interior portion within the domain. This is gamma interior and this is gamma exterior. Exterior is valid for exterior portion and interior is valid for interior boundaries. Now, we can discretize this particular domain using finite difference method. If we have finite difference method, then we can divide this into different parts and we can use Taylor series to approximate the function values at the nodal points. If we have finite volume, we will concentrate on the cell approach, and at the cell center, what is the value, we will try to utilize that for our calculations. Now, in these two approaches, we need support of this grid lines. Now, if we say that without the support of this grid lines, we want to solve the same problem, what should be our first step? Our first step should be to represent the same domain with number of discrete points. Internal portion we can discretize with number of individual points. Again, our boundary portion we can divide it into number of segments for 2-dimensional case and number of linear surface for 3-dimensional case. So, with this, if we start, then we can get some kind of approximation of the function, but in this case our generation of points can be structured or unstructured. Unstructured means the points can be randomly located or the points can be evenly distributed or equidistant within the domain. Now, if we use this domain representation like our finite difference approach, where in 2 dimension, if our central node is ij, this is I j minus 1 I plus 1 j this is I minus 1 j, this is I j plus 1. So, for the calculation at the central node nodal point, we have utilized the information from these 4 neighboring nodes in 2 dimension, that is I j minus 1, I plus 1, j, I j plus 1 and I minus 1 j. If we extend this for mesh free methods, we can define a general support domain in this case. Let us say initially this domain can be circular. So, within this circular domain for any central point we can have number of particles. These circular domain is called as support domain, and the center particle is represented in terms of the function values available at this neighboring particles within the support domain. Now, in this case we have seen that circular support domain, we can have rectangular support domain also. Let us say in x direction or y direction we can have different length values Lx, Ly, and depending on that we can consider a different number of points in different directions. So, we can see that with the change in the shape of the support domain, your representation will change. So, support domain accuracy of interpolation depends on the nodes present in the support domain, and dimension of the support domain ds can be written in terms of dimensionless size alpha s of the support domain and node spacing dc near the point under consideration. So, we represent this ds equals to alpha s into dc, where alpha s is 2 to 3 times or alpha equals to 2 to 3. That means ds equals to 2 to 3 times of dc. Support domain is 2 to 3 times of node spacing. Node spacing dc we calculated for our 1 dimension, 2 dimension and 3 dimensional case also. In this case, if nds is the number of nodes present in the support domain and ds is our support domain size, then nds and nas, nvs, these are numbers of nodes present in the support domain. So, dc can be calculated based on that. And interestingly, this is based on ds, this is as, which is ds is length scale, as is area, v is volume. So, approximate area approximate volume covered in this support domain. Field representation, mathematically field variable phi can be represented at any point xi within problem domain in terms of all node values within the support domain of xi. So, phi xi equals to wij into phi xj, j equals to 1 to n. So, n is the number of points present in the support domain, wij is the weight function at node j with respect to xi. So, we need to construct the shape functions. So, shape functions can be constructed by satisfying basic requirements as per Liu, suitable for arbitrary distributed nodes. Consistency criteria should be satisfied. Consistency is closely related to reproducibility in case of mesh-free methods. So, it should be reproducible. In case of our finite difference, we have seen that consistency means if you reduce our size of discretization, it should converge to the original solution. Obviously, that means the reproducibility is there. So, consistency is similar criteria here, suitable for compact support domain, and Kronecker delta property should be satisfied. That means, at if the function value is available and if you are considering the same node, it should be directly satisfied. So, Kronecker delta property, if xj equals to I equals to j, this is 1 or weight function is 1, and if I not equals to j, this is 0. So, in this case, partition of unity, that means within support domain your summation of this weight function, this should be 1, and linear field reproduction, this is for linear case. For in general nonlinear case also it should be reproducible. That means with multiplication of xj within the support domain, and if you take summation, it should exactly represent xi. Construction of shape functions, finite series representation methods, point interpolation method, moving least square or MLS method. Fx is any general function. This can be represented as a0 plus a1 p1x a2 p2x plus other terms. So, function can be approximated in terms of polynomials. Now, polynomial basis of order n can be written as p x, where x to the power alpha, such that modulus of alpha, this is less than equals to n, and modulus of alpha, this is summation I equals to 1 to d, d is the dimension, and alpha I, and x vector to the power alpha, this is x1 to the power alpha 1, x2 to the power alpha 2, x3 to the power alpha 3, x d to the power alpha d. So, if we consider one dimensional case, d equals to 1, n equals to 1. So, obviously, we have only 0 and 1, that means x to the power 0 and x to the power 1, we have 1 and x. If we consider dimension equals to 1, d equals to 1, n equals to 2, that is less than equals to 2, that means 0, 1 and 2. So, we have x to the power 0, x to the power 1, x to the power 2, this is 1 x x square, dimension equals to 2, that means 0, this mod alpha equals to alpha less than equals to 1, for n equals to 1. So, in this case 0 1 1 0 1 0 and 0 0 1 0 and 0 1, that means we are considering 1 x and y for this case. Similarly, for d equals to 2 and n equals to 2, we can have different combinations. So, 1 x x y x square x y y square, like that. So, this by changing dimension and n value, we can get different polynomial representations. So, in general, polynomial construction can be as per Pascal's triangle. So, we can have in one dimension 1 x, then 1 x x square, like that, 1 x cube. But if you are considering two dimensional case, we will have 1 x y, then combination like this. Now, this is Pascal's pyramid. If you are considering 3 variables in this particular case, then we can have 1 x y z, and on the other side we have x square y square z square and x y y z x z terms. In our previous case, we have seen that we can have constant terms with respect to 1 x y, and in this case we have 1 x y z. So, polynomial function, we have p 0 x vector, this one equals to 1, p 1 x, this is equals to x, p 2 x, this is equal to y. In this case, again p 3 will be added, equals to z. So, we can have constant terms, linear term, constant equals, that means 1, linear term, that means 4 terms, 1 x y z, and quadratic, that means considering 1 2 3 4 5 6 7 8 9 10, total 10 terms. So, with this polynomial representation or basis representation, we can represent a particular function in terms of series with a0, a1, a2 as coefficients with polynomial basis support. Thank you.